Alright, well, hello physical science students, and welcome to this video lecture, which is going to be about the periodic table and the trends that we can see on the periodic table. So to begin, we've been talking a lot about these things called valence electrons. And there is a trend that we can see on the periodic table with valence electrons, the number of valence electrons that elements have. And we kind of established this. We said that as we go down the periodic table, as we go down groups, valence electrons stay the same. But as we go across, valence electrons actually increase. Now, I want us to be sure that when we say that valence electrons increase, that we're aware of something. Through your periodic table project, you should have seen, because many of you chose to do transition metals, you should have seen that transition metals are goofy. They don't tend to follow the rules that we have normally on the periodic table with some of the other elements that are there. So, because of that, it's hard to say how many valence electrons some of these have. However, when we're taking a look at groups 1 and 2, and 13 through 18, we know exactly how many valence electrons those elements have. So in our first group, those elements, the alkali metals, they have 1 valence electron. In our second group, the alkaline earth metals, they have 2 valence electrons. Skipping these goofy transition metals, our group 13 has 3, group 14 has 4, and we can complete that all the way through. Now, really important note here is that these noble gases here, these noble gases, they have 8 valence electrons. That is a full outer shell. And that's really important for us to note when we start talking about some of these other trends. So, in summary on this slide, be sure that you know that as we move across these periods, that valence electrons increase, but that really only applies to these first 2 groups and these last 6 groups. The transition elements, or the transition metals here, stuff gets a little goofy. All right, so the first trend that I want us to talk about is atomic radius, and really atomic radius is just referring to the size of an atom. And that's the size of an atom of a particular element. Okay, and we came up with a trend here. First is if we move down a group, we said that the atomic radius increases. Okay, now why is that? Why does it increase as we move down a group or move down the periodic table? Well, that's because for every time we move down, okay, we go to a new period, we're adding an orbital. And we can call that a shell. We could also call that an energy level. Okay, because remember that in this group right here, the noble gases, they have a full outer shell. So what that means, and just reference the last slide, these all have 8 valence electrons. Okay, so let's, for example, take neon here. It has 8 valence electrons. Well, that's a full shell. So if we go to our next element on the periodic table, we have 1 extra electrons, so we have to add another orbital or shell for that electron to have a spot. Now, our other trend that we had for atomic radius was that as we move from left to right across the periodic table, or if we move across a period, our atomic radius decreases. And I think this one's a little bit more difficult to understand. Why, if we're adding protons as we move across a period, why is atomic radius decreasing? Well, the reason for that is protons have a pull on electrons. Just imagine for a second that protons and electrons are like opposite ends of a magnet. Well, what do opposite ends of a magnet want to do? They want to come together. Okay, they're attracted towards one another. The same case is true for protons and electrons. They're attracted towards one another because protons have a positive charge and electrons have a negative charge. So as we move across a period, because we're adding more and more protons, those additional protons add more attractive force to the electrons of that element. Okay, so the reason that atomic radius decreases is that more protons create more attraction. So essentially what happens is that atom becomes smaller and smaller. Those outer energy levels, they become closer and closer to the nucleus. Okay? So big takeaways here. Again, you probably came up with the trends, but we need to understand the reasons why. So as we move down the periodic table, or we move down a group, atomic radius increases because additional orbitals, shells, or energy levels, whatever you want to call them, they're added every time we move down to a new period. As we move from left to right across the periodic table, atomic radius decreases because as we add protons, those protons have more attraction to those electrons in that atom. All right, so the next big trend that I want to talk about is reactivity. Now, in that POGL, you should have learned about some other trends such as ionization energy and electronegativity. However, I think reactivity is probably the more important one for us at this stage. Now, with reactivity, there's actually two trends within our periodic table. So the first trend that I want to talk about is for metals. And when I refer to metals, I'm talking about these guys right here, okay? Our alkali metals and our alkaline earth metals. Okay, so when we move down a group, what happens is that reactivity increases. And when we move across the periodic table or across a period, reactivity decreases. Okay, I want to rewind a little bit. I think maybe before I even talk about this, you're probably asking, okay, Mr. Welch, but what is reactivity? Well, reactivity is dependent on how easily atoms gain or lose valence electrons. Okay, so reactivity, how easy elements gain or lose valence electrons. Okay, now I want us to remember here that the alkali metals have 1 valence electron and the alkaline earth metals have 2 valence electrons. Now, how many valence electrons does an atom need to have a full shell? Well, it needs 8. Which is going to be easier for these metals to do? Gain or lose? I hope you're all saying lose, okay? Because it's going to be very difficult for these metals to gain 7 or 6 electrons to get that full shell. They would much rather lose these, and it's much easier for them to lose these. So with that being said, metals lose electrons. Now, I want us to understand how these trends actually work. Why is it that when we move down a group that reactivity increases? Well, that's because of the size trends that we just talked about on the previous slide. So we said that as we move down a group, atomic size increases. Well, it's much easier for francium to lose an electron than lithium because francium is a much bigger atom than a lithium atom is. Okay, these protons in the francium atom have a weaker pull on those outermost electrons than the protons here in lithium do on its outermost electrons. So it's very easy for that outermost electron in francium to just go away than it is for that outermost electron in lithium to go away. The same principle applies here when we move across a period with metals, okay? As we move across, reactivity decreases, and that's because the size here decreases as we move across. The next trend that we can talk about for reactivity is for nonmetals. Okay, for nonmetals. And for nonmetals, I'm talking about this group right here, groups 13 through 17. Now, halogens are nonmetals too, but they have a full outer shell, so they just kind of want to stay put. They don't want to gain or lose. Okay, so for nonmetals, as we move down, reactivity decreases. Reactivity decreases. And as we move across our nonmetals, reactivity increases. Okay, so I want to take a look at this group right here, group 17, our halogens. Remember that these have 7 valence electrons. So it's going to be much easier, I hope you agree with me, it's going to be much easier for these halogens to gain 1 electron than it's going to be for them to lose 7. So with that being said, let's see here. Nonmetals, they want to gain electrons. Okay, they want to gain electrons. Now, again, I want us to understand why reactivity decreases when we go down a group. So when we go down this way, why does reactivity decrease? Well, again, going back to our atomic radius trend, when we move down a group, that size gets bigger and bigger and bigger. Okay, so it's much more difficult for this element here, astatine, to gain that 1 last electron than it is for fluorine, because these protons in astatine, they don't have as strong of a attractive force as these fluorine protons do on those outermost electrons, because astatine is so much bigger than fluorine. Okay, the same thing can be said for when we move across. Okay, when we move across, we know that our atomic radius decreases, so protons here have more of an attractive pull to gain that electron than these boron protons do to gain those additional electrons. Okay, now to keep these trends easy for you, just a quick tidbit that helps you to keep these straight. Francium is the most reactive metal. And fluorine is the most reactive nonmetal. Okay, so to summarize this reactivity page, this is probably one of the more confusing ones. Let's say that atoms had feelings. Okay, they can be happy or sad. Atoms are really happy when they have a full valence shell. So these noble gases here with the full 8 valence shell electrons with that full outer shell, they are very happy. However, these atoms, because they don't have a full valence shell, are not happy. Same with these ones. So they want to do whatever is easiest for them to get that full outer shell. For nonmetals, it's much easier for them to gain electrons, and for nonmetals, it's much easier for them to gain electrons, and for metals, it's much easier for them to lose electrons. Okay, so I hope that this was helpful. We're going to be covering this more in class in the coming days. Take care, physical science students.